Hello, here's a few more questions on circuits and charge and other such electricity related things. We've got a 12 volt 36 watt lamp lit to normal brightness using a 12 volt car battery of negligible internal resistance, as it would have to be if it's going to light it to normal brightness. The lamp is switched on for 1 hour. For the time of 1 hour, calculate the energy supplied to the battery. Right, so energy is watts times time. So we've got 36 watts and we've got 3,600 seconds for 1 hour. So that's going to be, well, 36 squared is 936 plus 360. And then we've got the two zeros to put on the end as well. So times 100. So that's going to be, what's that? 1296 with two zeros on the end. So let's say 1.3 times 10 to, what's that, 5 joules. So how much charge have we got passing through the lamp in that amount of time? So that is going to be our, well, Q is I times T. The current here is the watts divided by the volts. So we've got 3 amps for 3,600 seconds. So we're going to have 3 times 3,600. So a bit of an easier sum to do. So that 10,800, and that's coulombs. Right, the total number of electrons passing through the lamp. Right, so electrons, we're going to have to divide this amount of charge by the charge on one electron. Because if we had the charge of one electron had gone through and you divide by that charge of one electron, it gives you the count of electrons, doesn't it? So we need to divide this by 1.6 times 10 to the minus 19. And then that will give us our total number of electrons. Plus we know it's got to be a big number, so we've got to divide somewhere. I've got to go to the calculator this time. This is why I'm waffling a little bit. That comes out 6.75, so let's say 6.8 times 10 to the 22. Right, some nice calculations to get us started. Part B, the wires connecting the lamp to the battery are made of copper. They have a cross-sectional area of that. The current is that, which we already know. That's our N. All right, they're pushing us to a I equals ANEV setup here. Describe what is meant by the mean drift velocity of the electrons in the wire. Right, okay, so let's go full, the whole hog on this. So we're talking about the average change in displacement. Average change in displacement. So that's already covered the mean and velocity bits of it all. Average change in displacement, well, per second. I suppose that really gets us, we're going to get super picky, that really gets us to the velocity bit then, of electrons traveling along the wire. Traveling along the wire. Right, so that's done that. Calculate this mean drift velocity. So yeah, we've got our I equals ANEV, so we're just going to rearrange that. V is I over ANE, and then we're just going to stick everything in, which means we've got 3 divided by, so where's our A? 1.1 times 10 to the minus 7. Then we've got N is 8 times 10 to the 28. And then we've got E, 1.6 times 10 to the minus 19. So another calculator jobby on this one gives us 2.13. So let's say, well, 2.13 times 10 to the minus 3. So 2.1 times 10 to the minus 3 meters per second. That's our two significant figures, which is what we've had on these ones as well. Probably should have labelled those two significant figures up there. Right, so yeah, that was a nice one to get started, just doing some fairly routine calculations. Right, this has got quite a lot in it. Battery charger contains a microprocessor circuit, so it can charge an AA rechargeable cell at a constant current, 450 milliamps. Takes 4 hours and 40 minutes to charge a 1.5 volt cell from fully discharged state. Calculate the charge Q passing through the cell during the charging process. Right, so we're back onto another wrong sheet. Q equals IT. So we've got our current is 0.45 amps and our time is 4 hours and 40 minutes. Right, so that is going to be 280 minutes, so multiplied by 60 for seconds. Right, how are we going to go about working this out? I don't want to go to the calculator if I don't have to. So let's take 100 out of 280, make that 45, then we'll go mix numbers. 2 4/5 times 60. Right, that's going to make things a lot easier. So 45 times 2 4/5 is 90 plus 36. So that is 126 times 60, which means we're going to get 600, 720, 756 plus the 0. So there we go. Next part, figure 3.1 shows the cell of internal resistance 0.9 ohms, which they've marked on, connected to the battery charger. Assume the EMF of the cell is 1.5 volts. So that's quite an assumption when you're recharging these. I mean, that's the thing with cells. I mean, they put these things down as 1.5 volts. So if you read any of the packaging on these things or look up much about them, that's, you know, a sort of guideline. The PD or the EMF, it changes around a reasonable amount. So, but still, you know, we're just building up here and getting the principle of what's happening in recharging this cell. So yeah, we're just doing a constant 1.5 volts as an assumption. State whether the terminal X of the battery charger is positive or negative. Right, so we're putting light poles together here to try and push the positives back onto the positives. We're, you know, undoing what has been done previously. So we're going to want to have the positive here matching with a positive there and the negative matching with a negative. So we've got X being positive. Mark the direction of the current on figure 3.1. So we're going with conventional current and we're wanting to push things back. We're wanting to put energy. Oh, it's got there, give a reason of your choice as well. We're wanting to put energy back in the cell. Yeah, we're going to need an EMF on the battery charger which is greater than this 1.5 volts. And then that is going to overpower things. And for conventional current, we're going to have our positive charges going back onto the cell that we're recharging. So we've labeled the arrow, and then we need to give a reason for our choice, right? Which is probably easier said than done. But we're wanting to put energy back into the cell, let's do an IE, do work on the cell. I mean, it's quite, I don't really know how else to phrase that really, but yeah, we're wanting to put energy back in. So you're putting the like charges together and then you're doing work on them to do work on. So yeah, let's add that on actually by putting like terminals together. Yeah, just to add a little bit more on. I think that would suffice. Calculate the terminal PD between X and Y. Right, so we know it's got to be greater than 1.5. So we've got a net here, a net EMF. Our net EMF here is going to be equal to, that's going to be our VXY, as they've called it, minus the 1.5. That's how much sort of push, how much electromotive force that we've got in the clockwise direction. And that has got to be equal to the current, what was the current again? 0.45 multiplied by the resistance. The only resistance we've got is the 0.9. So that's just our V equals IR statement really, but you have to take the EMFs as being vectors. So we've got the VXY pushing clockwise, we've got the 1.5 volts pushing anti-clockwise, so that is our net EMF, and that is equal to the current multiplied by the resistance. So VXY is going to be equal to, what's that, 0.405 plus 1.5. So 1.9 volts to significant figures. So far, so good. The fourth one, show that the mean rate of increase of energy stored in the cell during the charging process is about 0.7 joules per second. Right, okay, so the cell, the power of our cell is the volts times amps. So P cell is equal to 1.5 times 0.45. So that's all we want actually, isn't it? Because they're just asking us for the power. So that we're hoping is going to come out at 0.7 or thereabouts. So we've got 1.5, 0.45. So 0.45 plus 0.225. So 0. I remember what I said now, 675, wouldn't it? Watts, about 0.7, which equals 0.68 watts to significant figures. Right, so yeah, that was quite sneaky. I mean, it's these ones don't come up massively. Yeah, they don't come up very often where you're doing these recharging ones. But remember, when we're recharging, that's when you are reversing the poles. So if you've just got a cell sat there, then everything's just flowing out of the cell. You need to reverse the flow of the current. So if you've just got your plus minus and it's flowing off like so, we need to change that direction of flow. So you need to have a greater EMF opposing it in order to push back, change the direction and undo everything that was done when the battery was discharging. Right, part B. Okay, so we need, what we got now, explain how you would determine experimentally the EMF E and internal resistance R of the charged cell. All right, okay. Include a circuit diagram of meters and a variable load resistor. Right. Okay, I'm really going to have to squeeze this in because I've not left very much space for this. Right, so we need the classic setup. We've got our cell. We're going to want the variable resistor. We're going to want an ammeter in series with everything, variable resistor with the arrow through it. And then we're going to need a voltmeter in parallel. I mean, with this, you can just take a single reading and stick it into the equation. It always seems a little bit of a cop-out doing that. And it's good to take multiple readings in order to average things out and check things. So let's go with our procedure then. We need to vary R and record, if I can spell it, record V and I. Obviously, you'll be turning these into more full sentences here. Then you can plot V against I, because we're going to be going to the internal resistance formula. So we've got the I is the EMF is equal to the current multiplied by the sum of those resistances. I mean, that's just a statement of V equals IR again. We just split the resistance into R, the capital R being the total resistance of the circuit and little r being the internal resistance of the cell. So we've then got, if we're going to rearrange that, well, actually, let's expand it out first, because I times capital R is V. That's what we're recording here, is the V. It's the only resistance we've got in the circuit is over the variable resistor. So I times the variable resistor is the reading on the voltmeter, plus I times R. So if we're plotting V against I, we are getting a graph of V is equal to the EMF minus I times R. So we're going to get something which is going a straight line going downwards, negative gradient. The intercept is the EMF and the gradient is the negative of the internal resistance. So we're just going to pull those off. This is why you don't really need to plot them out. I mean, you could record a few values and then just solve this equation simultaneously for a couple of them, because we need to get two values out of it, so you're probably going to end up with simultaneous equations. But it's quite nice doing a plot anyway, and it gives you a way of getting more of an average result. So anyway, let's run through that. You just got to turn this into sentences, but it's the same old procedure that you get for these experimental questions. Say what you're varying, say what you're recording, say what you're plotting, what equation you're using, and then that just by the time you've done those 4 steps and said what you're measuring everything with, as in we've got a voltmeter and ammeter, I mean that's then 5 things that you're saying every time. Vary, record with what, plot, equation. Easy to get the marks then. You're just sort of going through the motions. Right, so that is part B. The last part, which had better be quick considering how much page I've got left. We've got 6 volt, 2 watt filament lamp, resistance 18 ohms, lit to normal brightness. Oh, when lit to normal brightness. Connected in series to 4 1.5 volts each of internal resistance 0.9 ohms. So clearly it won't light to normal brightness using that setup. Explain using calculations why it doesn't light to normal brightness. Right, okay, with calculations, that seems a little bit unnecessary. Right, so how are we going to go about doing this with a calculation? And so, well, let's do a sort of counterfactual type thing. Let's try and squeeze it in down here. So if it's at full brightness, then we can say that the ratio of the voltages is going to have to be that we've got, what was it, for ratio of voltages is going to be in the ratio of the resistances. So we've got 18, must be in 18 ohms to internal resistance. We've got 4 0.9s, so 3.6. We have to have that ratio in order to have it at full brightness, because at full brightness it's 18 ohms. So that would be our ratio of voltages, right? So 3.6, that's why they've given us these 0.9s. It makes it quite easy. So that's a 5-to-1 ratio. So if you've got 5-to-1 ratio, we can say, well, therefore we'd only have 5 volts across, not that I can fit it on the screen, across the bulb. In which case you can say, therefore, it's not at full brightness. So it's sort of a counterfactual thing of saying, well, if it was at full brightness, this is the setup we would have. We'd have that resistance, which means we'd only have 5 volts, which isn't 6 volts. So there's probably other ways of going about it, but that's the way that springs to mind for me at the moment. So this is what we require. This is the definition of full brightness, this setup of voltages, but it then doesn't work. It is found that by adding more cells in series, it is possible to make the lamp light to normal brightness. Calculate the number of cells needed. Right, well, let's just flesh out this calculation then, and that will give us a way of working out what we want. So we need the ratio of these resistances then. So we're going to have, we're dividing these. So we need to do 18 divided by 0.9 times n, where n is the number of cells that we've got in this battery. And then that we need to divide by, well, that same thing, 18 over 0.9n plus 1, because that's just what I was doing here. This is how we turn a ratio. That's just a statement of how we turn a ratio into a fraction. So we're saying that this would have been the 5 at the top, and then at the bottom, we've got the sum of the 2 bits, the 5 plus the 1. So that's just a statement of what a ratio is. We need to then multiply that, because we've got that fraction of the total EMF, which is 1.5 times n, and that would have to equal 6. Now we just need to solve that for n. So that n will cancel with that n. 18 over 0.9 is 20. So we've got the same thing there, but I'll deal with that in a minute. Divide by 1.5 gives us 4. Multiply through by the denominator, we're going to be left with 20 is equal to 4 times, well, 18 over 0.9 is 20, so 20 over n plus 1. So let's take we'll expand this out, multiply by n, take that 4 off. We're going to end up getting, I know this is going all over the place here, but 16 by the time we take that 4 times 1 off of the 20 will be multiplied by n as to be equal to 80. So n is equal to 5. So we just need one extra cell. It looks more complicated than it is doing this approach, just because of the slightly messy setup of turning a ratio into a fraction. But that's all that is. So it doesn't look anywhere, it's not actually anywhere near as bad as it looks. It probably looks worse as well, in the fact I've cluttered up the page so much. But yeah, if you just work through that one on, with pen and paper, you'll just see that that is just a ratio calculation there. Right, that was quite an involved question, that. A lot going on there. Right, I'll do one more though. So I've only got one more in this set. Kirchhoff's laws can be used to analyze any electrical circuit. State each of Kirchhoff's laws and the physical quantity associated with each law conserved in the circuit. Right, this just comes up so often, so I'm not going to write it all out. Kirchhoff's first law, this is the conservation of charge one. The sum of the currents into a junction is equal to the sum of the currents out of that junction. Kirchhoff's second law, that's the conservation of energy one. So the sum of the EMFs is equal to the sum of the PDs around a closed loop in a circuit. So those ones should be second nature by the time you've done all your revision on this. Right, so now we've got a circuit analysis. We've got a 45 volts, that's on the picture, don't need that. Negligible internal resistance, that's fine. 3 resistors, yeah. R1, R2, which they've got on there, 750. Current in the resistor, yeah, they've marked that. Current in that, they've marked everything on the picture, so we've got nothing else. It's all there on the circuit diagram. Calculate the current I in the 750 ohm resistor. Right, so this is Kirchhoff's first law. We've got 0.03 coming out, so we must have going in, so we must have 0.03 coming out. So it's going to have to be 0.02. And they've put zeros on the end. They've gone for that extra significant figure, so we will follow them. The PDV across the 750 resistor, right, so what have we got then? So we've got 0.3, oh, we got 0.2, oh yeah, 0.2 going through it. So we've got the V, we got the R and the I. So V is equal to 0.02 times 750. So that's going to be 1500 divided by 100. Yeah, so 15 volts. Cool. Resistance is R1 and R2. Right, well, R2 is going to be easier. It's got half the current going through it compared to the 750 one, so it must be double the resistance. So R2 is going to have to be 1500 ohms. And then, I mean, you can also get that off of the fact that we've got this here. I mean, that's saying we're doing V divided by I. So that's 15 because it's got the same potential difference as the other one divided by 0.01. So that's it. If you actually want to put the calculate bit in, then we've got that. So what's then happening in R1? So R1, well, we know that the PD across R1 is 30 volts, because if we've got 15 across here, then we must have 30 across there. So R is going to be 30 divided by 0.03, which is 10 times 100, which is 1000 ohms. Right, so that was all good. And yeah, we go over to the final sheet. They've now removed R2. They're replacing it with an LDR. We've got a light dependent resistor. Draw the circuit symbol. Right, so LDRs, that's where we get, so we draw in the resistor symbol, we put it in a circle, and then we draw a couple of line arrows coming in at it. That's our LDR. Resistance of the LDR falls from about 1.5 kilo ohms to, which is what R2 was, down to 400 ohms as light intensity increases. State and explain without calculation how the potential difference across 750 ohm resistor varies as the intensity of the light incident on LDR increases. Right, so we've got then that the R LDR will decrease. So the R parallel, that's going to go down. And if we're dropping the resistance in one branch, the resistance overall is going to drop down. So we can then say, well, V parallel is going to drop as well. Because, well, let's put in brackets because R1 is fixed. R1 fixed. You know, if we're reducing the PD, reducing the resistance, I mean, across this branch, it's going to get a lower cut of the PDs. So, yeah, that was simple enough. Last bit. Suggested that the LDR in the circuit is used to monitor changes in light intensity. Draw a suitable electrical meter in the LDR branch of the circuit to measure these changes. Right, well, you could do this either with a voltmeter or an ammeter. It doesn't really matter which one you're going for. Let's say we're going to stick an ammeter in, but the more or less the same things apply to the answer here. We got, state the meter you've chosen and suggest a sensible maximum scale reading, right? So we're going for an ammeter. Right, maximum reading. Well, we're going to get a maximum current when we're down at 400 ohms. So what current are we going to get if we've got 400? So this was 1,000, wasn't it, here? So we need to get R parallel then. So R parallel. So at maximum current, we're going to get minimum R LDR equals 400 ohms, because that's what they told us it was going down to. So R parallel will be, we have to do our parallel resistor thing. So 1 over 750 plus 1 over 400. Take the reciprocal of that, and that's not easy numbers. So I'm going to have to go to the calculator on that one, sadly. So that comes out 261 ohms. So around about a quarter of the other resistor. So we're going to get give or take. Therefore, we're going to have around about 9 volts across the LDR when we get to that level. So our maximum current is going to be roughly equal to that voltage divided by the 261. So, well, that's about a third divided by 10. So it's going to be 0.03, give or take, let's say, and a bit more amps. So we want a sensible maximum reading. So let's go for 40 milliamps. That sounds reasonable, I think. 40 milliamps. Have that as a maximum. That was quite a bit to work out at the end there with all of that, but yeah, a nice circuit analysis question. So those ones are normally nice to see in an exam paper.